Good afternoon, everyone. My name is Peter Arnold. I'll be your chair for this session, and welcome to presentation session 1. We have 3 exciting talks up for you this afternoon, all on Python. We've got a bit of Django, a bit of Wheels, and then we've got a case study. The first 2 will be walkthroughs. The third one will be a talk. If you could remember that this is a session, this session has been recorded and will be up on YouTube later. Each of the talks will be 20 minutes. At the end of those 20 minutes, we'll have 5 minutes of questions. If you could put your questions into Slido, the link will be put up on the chat if you haven't seen it already. Yeah, we'll do that at the end of the session. So, okay, without any further ado, I'll hand over to the first speaker, who is Terry Forey. We're talking about Django. Over to you, Terry.
Thank you. Let me just share my screen. Okay, so hopefully you can all see that. So hello, yes, so I'm talking about how to set up a Python web application, Django beyond the tutorial. So a little bit about me. I have been working with Django since 2017. I'm currently a full stack software engineer with Wellcome Trust. I'm also a freelance RSE, and I'm also a trustee of the society. So you're probably going to see quite a lot of me at this conference. So what we're going to do today is we're going to have a very quick run through some Django basics, looking at some settings and layout for your project, looking at the user model, and then lastly, we'll try and squeeze in a little bit of how to add NPM and JavaScript and styling into your Django. Okay, let's get going. So what I've done is I have pre-recorded some videos, which I'll sort of talk over as we go. So first of all, things to create your Django project, you need a virtual environment. So I'm going to use conda here, and what I'm going to do is I'm going to create a new environment called SeptembRSE, and I want Python 3.9 and Django. So what this is going to install is Python 3.9.6 and Django 3.2.5. Cool. So let's get those installed. So that will download them and install them, and then we can activate our environment. Now that we've got that, we have access is the Django admin program, and that we can use to start a new project, which we're also going to call SeptembRSE. Takes a few seconds to run, and what we'll have to do is create a new folder which we can open up in our IDE. So this creates a file called manage.py and a folder called SeptembRSE. And this has got a whole bunch of different input entry points and some settings file and a sort of project-wide URL file. And it's really everything to do with the project itself. Okay, there's no here thing to create views. What we need for that is we need to create an app. So we use that manage.py script, and we use that. It's got lots of different potential things you can do with it. We're going to use that to start an app. And because this is our first app, and it's our app that's going to be really the core of our project, we're going to call it core. So that will create this folder here, and what we can see is here we've now got files to set up our models, our views, and everything that really is our web application. Okay, so that is all in the folder core. And to make sure that Django knows where it is and to be able to use it, we need to add that app to the installed app list that is in our settings.py file. So once we've added it in, Django should now be able to find that folder and use it. Brilliant. What we can do now is you can use that manage.py script to run our test server. So this will come up with a warning at this point, but do not panic. And at this point, do not run the little code it tells you to run that will fix that error. Okay, we're going to come back to that in step 3. But our Django project is now up and running. So if we go to localhost 8000, our install is working successfully. Ah! Okay, so, oh, no, don't play it again. Next slide. There we go. So Django, it is quick. You can get up and running very easily. It is scalable, okay? Django does power Instagram. Django is an all-included or batteries included framework, so it will do absolutely everything for you out of the box. It has an admin view. It has way of building, it has an ORM, so you can control your databases and everything all that. Okay, it kind of does a bit of everything. But it is quite opinionated, and as you saw, there's quite a set sort of architecture and layout that comes with it. So let's look at that, settings and layout, and how to configure your project. Okay, we have another little video. So what we have here is, what we're going to do is, first of all, we're going to look at settings. So what we're going to do is we're going to create a new directory or a new Python package called settings inside that project directory. Okay. And we're going to move the settings.py file that's been created automatically into that settings package. So now we have it here, and what we're going to do is we're going to rename it to base.py. That's because this is the core settings or the base settings that apply to my project in any environment. Okay, so these are the general settings everywhere. Now, because we've moved it down a project, we need to just update the base directory. So make sure that it's pointing to the right parent drive still. And what we can add then is we can add our environment specific settings. So we can have a dev.py and we can tell it to import everything from those base settings. So everything here will get imported into our dev.py and then we can tweak it. So for example, if we wanted to add an app that's only available in dev, we can do that here, like the Django debug toolbar. We can also have a test.py. So this will be settings that are specific to our test environment. So again, they import everything from base and then tweak it. And lastly, of course, we can have our pod.py. So this will import everything from base and then we can tweak it for our production. So the first thing we might want to do there is set debug to false. So this is a nice way of sort of setting up your environment files that basically your different settings, different environments that will run off the bat. And there's lots of different things you might want to tweak, like the allowed hosts, secret key, your database connection settings, and you can put those into those environment files. Okay, cool. We can just quickly test. Oh, what we need to do then is we need to make sure that our entry points are pointing to the correct settings. So the manage.py is the file and the script that we use in dev. So we need to point that towards settings.dev. Whereas our WSGI and ASGI files, those are our entry points that are used in production. So of course, they just need to point to .prod. So that's .prod file. If we run our server again, it's all happy, there's no errors, happy days. Now, the next thing we're going to look at is templating, okay? And this is about where do we put our templates? And the first, there's two different places we want templates. The first one is the project-wide templates, okay? So these are things that are going to be used in potentially multiple different apps and across the whole project. So we do that in a top-level directory called templates, and we're going to put in a file there that's called base.html. And I've got one here that I've already done. So this is got a few different bits and pieces in it. It's got a link to Bootstrap CDN. We'll come back to that later. It's got a whole bunch of different blocks, some snippets, and all sorts of bits and pieces that we can replace and extend and sort of do things to. We might also have a version of this which doesn't have that top bar bit. It doesn't have the top menu. It doesn't have the messages. And this might be used, for example, for password reset kind of form or something like that. So we've got a couple of those different bases. We're also going to add in some snippets here. So again, these are snippets of templating that could be used in multiple places. In this case, we're going to have one just for our top bar. So that's our nav bar, so it's quite easy to get to. And again, this is something that's used across the whole project and it's not app specific. We also might, at this point, want to override some templates that might be coming in from different apps. So in this case, I'm overriding the registration login form, okay, to use my own form. Now, to make sure that our Django can find this new folder we've created, we need to add it into our base settings. So in the directories thing here, we're going to have base directory, and we're going to add in templates. So it's going to point towards that top level folder. And because Django reads these things in order, it's going to read that top level folder before it looks in any app directories. Okay, so that means that those things are going to be read first for anything else. That's why they're top level. But we still do want templates that are app specific. Okay, so we're going to have a templates folder in our app. And what we're going to then do is have another folder inside that that's also called core. Okay, it's the same name as the app. And that feels really repetitive, but sort of trust me at this point. What we want is we want clear namespacing. So if I have a folder or an HTML file in here called index, for example, if I have another app that also has an index.html, Django is just going to load whichever one it finds first. So you could have conflicting templates here. So what I'm going to do is I'm just going to write a quick HTML file. It's just going to override that block content and just say hello. I then need a view to be able to surface that. So I'm going to have a view called main. It's going to return the request, and that file should actually have been called main. Let's just rename that. So we've got a function called main, a view called main that's returning a template called main. We then need a URL. So again, we're going to have a URLs file that's specific to our app. Okay, there's a URLs file that comes with the project directories, but we want some specific to the URLs and views for this app. So let's create this one here. So we import our views, we set our URL patterns, and what we're going to say is our top level path is going to have that views.main, and it's going to use the name main. So you'll spot it here that our URL, our view, and our template all have the same name, okay? And it just really helps you later on when you've forgotten what everything's called. So give them all the same name. And what we can do then is in our project level urls.py, we can include the URLs from our app. So again, at the top level path, we're going to include the core URLs. And also at this point, I'm just going to include some of the default authentication URLs that come with Django. So that's django.contrib.auth.urls, and I was going to put those under accounts, just because there's no point rewriting the wheel. Django comes with a whole bunch of forms about resetting passwords and if you've forgotten your password and things like that. So let's use those. So if we refresh and open our browser, hey, it's working. We've got our Hello SeptembRSE working. We've got our snippets of being shown because we've got the top bar with home and login. If we have a look at the login page, okay, at this point we hit an error, and that's because the login form that I overwrote in the registration is actually using this thing called Crispy, and this is just a nice little library that I quite like that allows you to work with Bootstrap, and it just sort of makes your forms render nicely. So quickly install that. It's not important to this, so I did it very quickly. But yes, now refresh it and everything looks beautiful, fantastic. However, we are still going to hit a problem when we actually try and use the form. And that's if we try to log in, we're going to hit an error because there's no such table. And that's because we still have this issue about unapplied migrations. So just to figure out that settings and layout section, we're preparing ourselves right from the very beginning for working in different environments, for working in dev, for working in test and production. We're being careful about organizing ourselves and getting that namespacing set up early so that our templates are organized and we know which template is definitely going to be used. We're also making most of the included forms and things that come with the Django authentication. But we still had that problem about when we hadn't done those migrations. So now we're going to have a quick look at the user model and getting ready for that authentication. Here comes another video. So where were we? We were here, and what we want to do is we want to go into our app models file, and we're going to import the abstract model, which is the sort of base class that Django uses by default for user abstract user. So what we're going to do is we're going to create a class that inherits the abstract user. And at this point, we're not actually going to do anything to it. It's just there so that if we need to in the future, we can expand upon it and change things. And because we're using our own user model, we just need to make sure it's available in the admin views. So we're just going to add it in here as well. And we're going to use the default way that Django will view and let you interact with that user model, which is the user admin. So we just register it in there. And then last thing we need to do is make a change to our settings. And we need to add in a setting that tells it, this is the user model that we want you to use. And that setting is called auth user model. And we point to the name of our app and the name of the model. Core.user. Okay, so now what we can do is we can run manage.py make migrations. Okay, and that's going to tell it to look at the models and decide how they can be turned into database tables. That will create a migration file for us, and then we can migrate. Okay, and this will actually put that table into the database as well as all of the other apps that we're using by default, like the Django authentication ones, admin sessions, etc. Now let's run our dev server, have a look at our page. And hooray, we have a form. Let's try filling something in. And now we're not getting an error because it can't find the table. We're getting an error because that user account doesn't exist. As expected, we haven't created it yet. But that's fine. So tweaking this user model, it's really all about making things future-proof. If you don't do this in the beginning, before you run that very, very first migration, you no longer have access or ability to edit and change the user model because it's by that point, everything else that you've migrated is set up to use the default Django user model. So if later on down your project, the researcher or whoever wants to go, actually, it'd be really nice if we had some way of knowing what institution our users were from, and you wanted to add that into the user model, you can't do it by this point. You're going to have to end up creating a one-to-one table and some profiles, and it gets a bit messy. So even if you don't think you're going to be changing that user model now, this is just a really nice thing to do at the very beginning when you start a project. That means that should things change, you're covered already. Right, next up is NPM and bootstrapping and JavaScript and styling. And I'm just using Bootstrap as an example here. This could really be any kind of JavaScript library or package that you wanted to add in. So let's open up our base templates. What we want to do is we want to place the CDN with our own customized version of bootstrapping, or sorry, Bootstrap. So what we're going to do first is we need to initialize NPM. We need to get it running for our project. So we want npm init-y. What that will do is it will create this package.json file, and then we can install the things we need. So we're going to install Bootstrap, and we're going to save it as a dev dependency. We're also going to install Parcel. And Parcel is by far the best compiler and bundler I have come across, and I will shout its glories from the heavens if I can. And so yeah, so we're going to install Parcel Bundler. Parcel Bundler is actually version 1, version 2 is now out and is good to go. You just want npm install Parcel. So what that's done is it added into our package.json, and it has installed those programs into our node modules. What we need now is we need a couple of directories. First of all, we need our output directory. So this is where our compiled, bundled, ready to be served static files are going to live. We're going to call that static. Okay, we also need a location which is going to contain our JavaScript, our Sass files, everything that's sort of pre-compiled, okay, and needs to be basically our working directory. So in here, we're going to have an index.json, sorry, index.javascript. And in here, what we're going to do is we're going to import Bootstrap from our node modules. So this line here will just import all of Bootstrap from Bootstrap into this JavaScript file. Now we're just using everything from Bootstrap here. You could be quite specific. You could just import just the parts that you really needed, but we're just going to import the lot. So once we have that, what we can do then is we can add a custom.sass file or .scss. And in here, we're going to import all the things from Bootstrap, the actual sort of styling things from Bootstrap that we want, okay? And I just copied this over from a previous project, which actually was slightly differently formatted, structured, so I just need to tweak that. So yeah, so import from node modules, and it'll import all those different things from Bootstrap that we want to tweak. And we're going to come back to those variables at the top in a second. So now we've got these two files, what we need to do is we need to be able to compile them and bundle them and get them ready to be served. And for that, we use Parcel. So in our package.json file, we're going to create a parcel watch command. And we're telling it, take these two input files and output things into the drive called static. That's it. That's all you need to do for Parcel. We're also going to have something called build, where we're going to tell Parcel to build those exact same two input files and output them into the static directory. And that, instead of watching them and rebuilding them whenever it detects a change, that's just going to actually build them ready for production. Okay, so once everything's sort of, we've reached a new version, we're ready to launch, we can run build, and it'll be good to go. Now, I actually had an error in my JSON here, so we'll just fix that. And now we can run npm run watch. That's going to run Parcel watch, and there we are. It's built it. Nice and quick and easy. Have a look in this static directory. We now have custom.css, custom.js, and index.js. So presumably some of that SCSS files that we were importing from Bootstrap contain some JS, and so Parcel just read it, understood it, and decided to compile it for us. Lovely. What we now need to do is make sure Django knows where that static file directory is. So we need to tell it base directory /static is where those static files are that we want it to serve. And then what we need to do is we just need to put that into our templates. So in our base.html, what we're going to do is we're going to change this link, which is currently pointing to a CDN, and we're going to change it so that it's looking at our own served static files. So we use Django's sort of templating for this, template language. So static, that custom.css file. And since Parcel created it, we might as well also serve the custom.js file. So we add that in as well. Fantastic. And then down at the bottom, we can replace our bootstrap bundle.js with our static index.js. And like I say, Bootstrap is just an example here because it's just a templating package that styling package that I quite like. This could be a Vue app, this could be a React app, anything you like. It will just work the same thing, and Parcel will just figure it out for you. So cool. Let's get our server running. So server's running here. Fantastic. Let's refresh our page. It's working, and we can see that in those outputs, it's getting 200 responses. All good, okay, from our new static files. And now that we have this, we can start tweaking things. So we can change some settings. We can change some options that come with Bootstrap that will just subtly tweak our website. And so what we do is we're going to make those changes there in that SCS file. As soon as we hit save, Parcel sees those changes and rebuilds. And ta-da! Our web page now looks different. We've got purple colors. And that's it. Okay. So, I clicked on the wrong thing. There we go. Parcel. It's quick, it's a very simple bundler. I found it 1,000 times easier to use Parcel than Webpack and Gulp and all those other things, which have always just confused me as to how on earth you're supposed to configure them without copying and pasting. I don't know. Things like adding bootstrapping. Yes, it's a very recognizable sort of styling template, but you really only need to make a few minor changes to make your app look just subtly different enough and just a bit unique. And to be honest, it's so quick and easy to put in. And as an RSE, we don't often have time to spend on styling and making things look beautiful. So I would probably recommend going for that. And that is me. I kind of run through that. I'm sorry. Thank you. We'll go to the questions. If anybody wants to have a look at this repo, it is on my GitHub drive. Have a look at it, terry/SeptembRSE. And a big thank you to the Django Unstuck workshop by Johan Spillman, which was at DjangoCon. I'm wearing the t-shirt today, which was really inspired me to do this talk. And lastly, go off and read the Django docs because they are awesome. And I shall stop talking.
Brilliant. Oh, thank you, Terry. That was fantastic. We do have a couple of questions. If I go down in order in which they've been upvoted, the first question is Parcel the next Gulp? Yes.
Yes, that's a very simple thing to answer. I have tried using Gulp, and to be honest, I have still not managed to get it installed and working with me actually understanding what it does. And the great thing about Parcel is that you don't need to understand what it does because you just point it to the files and it will do it. And I was pointing it to JavaScript and this SCS files directly. You can actually just pass it to the index HTML, which has those in it, and it will do a hot module replacement, and it will just go, oh, that's the file that you wanted. Sure, I'll compile that, bundle it, and then replace your index.html with the final version. So yes, it's by far the next goal.
Okay, cool, thank you. Next one up is from Anonymous, whoever that is. They look like a lot of setup. How did you learn to do this? And what are the good getting started guides?
I think read the Django docs. The Django docs has got a great tutorial which will go through the actual nuts and bolts of how to run Django and the views and the models and things like that. And then these steps, I kind of just picked them up as I went along. There are some good blogs out there. I mean, feel free to take my repo and just fork it and make your own version. There's some complicated cookie cutters that will do a lot of the setup for you, but to be honest, I found them a little bit overbearing sometimes and too many options available. But other things I would recommend is there's some great books out there about Django and getting started, and also come along to Django conferences because they are a lot of fun and they'll teach you.
Cool. Another question, what are your thoughts on using Django to design a database rather than designing the database from scratch?
Good question. I think it's one of those ones that just goes back to the whole, it depends on what you need and what your project is all about. I'm quite happy to set up my models in Django. If it's not something that's particularly complicated, you can pretty much do everything you need in Django. If you even need to write quite specific SQL queries, you can actually just do that in sort of raw SQL if you need to. And then everything just kind of works, and it's very easy to update it because you have that migration system built in. a project I've been working on lately, we have done the database from scratch, and then it's a case of, well, how do we update everything on production? And we have to write our own migration system, and we kind of ended up rebuilding Django, and there was not much point in doing that.
Okay, thank you. And one last question. It looks like it could be a controversial one. So can you do this in one word as we're out of time? And what's your view on Django versus flaskor pyramid?
I prefer Django. It's my favorite. I like the fact that it comes all inclusive, mostly because pretty much every project I've ever had to do as an RSE has required a database. It's required an admin view. It's required all the things that come out of the box with Django. So I haven't really felt the need to have a Flask app, which is a bit more lightweight, because I'm just going to have to build all those things or add all those libraries into it anyway. And as for Pyramid, I've only used that on one project and I did not enjoy it. So, and I can't really put my finger onto what it was I didn't enjoy, but I just didn't enjoy it. So I hope
sounds fair, doesn't
it?
Excellent. Well, thank you very much, Terry. And that's all the questions for that. So thank you for that. I should have mentioned earlier on that we will be having a 5-minute comfort break after Thibaut's talk next. He's got a walkthrough for us. Thibaut's from Leston is from Oxford University and is going to talk to us about Python wheels. Over to you, Thibaut. I hope.
Hi, can you hear me?
Yes, can hear you now.
Yeah, I'm trying to share my screen, but the resolution is not. If I double, here we go. Okay, can you see that?
Yes.
Okay, that's great. Good. So thanks everyone for joining. My name is Thibaut Leston. I'm a research software engineer at the University of Oxford. I'm part of the kind of the central research software engineering group here at Oxford. And so we work across the whole university. And as you can imagine, a lot of the projects are Python projects. And so today what I wanted to do is talk to you about some kind of very fundamental aspect of packaging Python project, and so namely Python wheels. Because whenever you install a package that's not already installed on your computer using pip, for instance, then pip is going to go and talk to the Python package index and download the package that you want to install as one unique file, and that file is a wheel file. It's got that extension .whl, right? And so it contains everything that pip needs to install the package on your machine. Today, what I want to do is basically divide this walkthrough in two main sections. The first one is we're going to have a look at the simple example package, and we're going to see how we can build a wheel for it. And that's going to be, although I'm using GNU Linux today, that's going to be quite independent of that, and the same steps apply for, well, whether you're running Windows, Mac, or Linux. Then the second section is going to be specifically looking at building wheels for GNU Linux systems, because in that case, you'll see that we have a little bit more work to do in order to make sure that the wheel that we build can be actually used across many Linux distributions. So as I said, these two things, we're going to look at them from an example package, an example Python package that I put together. It's a fairly simple package. It consists mainly of three things. The first thing is a C++ extension. So it's literally C++ code, and that's going to be compiled into a binary extension module. And that C++ extension has a dependency. It's both a build time dependency and a runtime dependency on some other C library. And that's a library that's completely external to our package here, but it does have a dependency on it. And then the rest of the package is these two Python files, the init file, and then some kind of a Python module that uses the extension, right? So that's the layout of the package. Just to give you just a word about how this package is built, that Python C++ extension is written using PyBind 11. That's a C++ library that makes it, I find, relatively straightforward to interface both Python and C++. Right? Then that C++ extension, it's built using CMake, and that's a choice that I made. There are other ways of doing this, but I find that CMake is actually really good at interfacing with Python 11, and that use case is very well documented in the documentation. And then lastly, the whole thing, the whole package is built using scikit-build. And scikit-build is a Python package, and it's basically an add-on on top of setup tools that makes sure that you can use CMake kind of like seamlessly with setup tools. Good, so let's pretend that we've been working on that package, we're quite happy with it, and now we want to share it with our friends, right? So in order to do this, to share it, we're going to build a wheel. So building a wheel is actually can be done in only one command. It's a bit like, Python setup.py install, but instead of install, you say Python setup.py bdist_wheel, and that's going to build the wheel file for the package. I'm going to let it work for a few seconds. And now it's done. And if I look at the current state of my directory, I see that I've got a new directory called dist. And inside that directory, I've got my wheel file, and that ends up in .whl. Okay, I just want to go and show you, have a little look at what just happened. If we scroll up and then have a look at the output, the first thing that we find is some output from CMake. Okay, and that is actually the compilation of the C++ module. So we see that this d.cpp file is actually turned into C++, like a shared object, a compiled extension module d. And so now in Python, you can say import d. And you get access to the code inside the extension module. So that's the compilation of our C++ module. Now, if we scroll down a little bit, then what we find is a bunch of creating temporary directories, moving files around. Ultimately, what happens, if you take a little look at that, what you'll find is that both the compiled extension module and the Python files end up together inside that temporary directory called wheel, right? And so that's the second step. And then now the third step is writing some metadata about the package itself and about its build. And so all of that ends up inside that wheel directory. So far, that process is identical to what would happen if you were installing that package on your system. The only difference at this point is that instead of these files being copied inside your local package directory, they are actually installed inside that temporary wheel directory instead. And now the fourth and last step of this process is to take that wheel directory that contains literally an installed version of the package and make it into an archive. And then what we end up with is a wheel. And that wheel is literally just an archive. And it's actually a renamed zip file. And you can verify that if you try and list the files using unzip with the wheel file, then you can see that it actually contains the installed version of the package. It contains the Python files, it contains the compiled extension and the metadata. And now what we can do is take this file, give it to our friend, and they can use pip to install it. And then the only thing that pip has to do is extract the archive and then copy the files into the right place in their computer, right? There's no need for pip at this point to run the setup script, right? And you can see that the setup script, the setup.py, it's not there. It's not even in the wheel because it's not needed. The immediate benefit of that, in our case, is that our friend, they don't need to worry about CMake. They don't need to worry about installing that C library. They don't need to worry about scikit-build, etc. in Python 11. They get the wheel, they pip install it, that's done, finish. They can use the package. There's one downside though, is that you can see that the wheel, the name, actually is very specific to the Python version that I used, 3.9, my current operating system, that's Linux, and my current architecture. And that's because the package that we just built contains some compile code. And so if your package contains compiled extension modules, then you're going to have to build wheels for each Python version, for each operating system, for each architecture that you want to support. Now, if your package is purely Python, that's great. You don't have to worry about this. Your wheel is going to be as portable as Python is, and that means really portable. But if you do have compiled modules, you're going to have to think about compiling your wheels several times. Okay, so far this process is the same on Linux, on Windows, on Mac. The only difference is that you're going to end up with a different platform tag depending on your operating system and architecture. Now I'd like to focus on the specific case of building wheels for GNU Linux systems. Because in this case, we're going to have to do a little bit more work in order to ensure that the wheel that we build is usable on a large range of Linux distributions. On GNU Linux systems, virtually every executable or shared libraries, they have a dynamic, a runtime dependency on the GNU C standard library, right, that we call glibc. This means that whenever you import a compiled Python module, then that Python module at runtime is expecting to be able to find some code, some compiled code somewhere on your computer for the GNU C standard library. Now, glibc, that standard library, well, newer versions are guaranteed to be, are not guaranteed, newer versions of it are not guaranteed to work, to be compatible with older versions. And that's a problem for us building wheels on Linux, because that means that if we build our wheel on, say, the latest Ubuntu, that has a fairly recent version of glibc, then it's actually quite unlikely to work on another Linux distribution, say Debian, that has an older version of glibc. And it's very, very unlikely to work on any older GNU Linux distribution like CentOS 7 or that were released about 10 years ago. It's not going to work because we compiled our project with a newer glibc. Now, the good news is that the opposite is true. Older versions of glibc are guaranteed to be compatible with newer ones, which means that as a Python packager, if you manage to compile to build your wheels inside an older system that has an older version of glibc, well, it's going to be compatible with any Linux systems that has a more recent version. Right? So that's the trick here. So does that mean that you need to go and find that old CentOS 5 CD-ROM in order to install it and then build your wheels? Well, actually, no. Well, you could do if you think that's fun. That might be fun. But if you don't have the time, then you can look at the work of a working group of people that is named the Python the Python Packaging Authority, and that's a group of mostly volunteers, I think, probably, and they maintain the Many Linux project. And at the core of that project is a set of Docker images that each correspond to a specific version of glibc, of the GNU standard C library. And then these images, they are meant for you to use them and build your Python wheels in them. So I'm just going to demonstrate how, show you what that looks like using Many Linux 2014. That's based on CentOS 7. That was released, you can guess, in 2014. So let's have a look at that. Back to my terminal. I'm now going to switch inside that Docker image. So now I'm inside that Many Linux 2014 Docker image, and we're going to build our wheel. These Many Linux image, they come with anything you need to build wheels. So in particular, you get a lot of different Python versions, both CPython, and also PyPy. So what do we have to do to build our wheel? It's the same process. The first thing we have to do is install that C library that our extension depends on. I'm not going to do it because I've already did it in order to save a bit of time. So it's already installed inside that Docker image. And then we build our wheel, right? You can also build a wheel using pip directly, right? You can say pip wheel dot, and that's going to build a wheel. It's a wrapper around Python setup.py build wheel. It's the same thing. Same, I've already done it, and so I'm not going to do it again. Actually, if I move to look at the files in that Docker image, so an underscore here, you can see that the wheel is there already. Okay, so does that mean that we are done? No, because you see, if you look at the name of that wheel, of that file, then it's still saying Linux, right? And it's not containing any information about the level of portability of the wheel. What we'd like to have is some kind of a keyword that says, well, that wheel is compatible with that version of glibc, right? So we want to have a more accurate, precise platform tag. In order to get that, we can use a little Python tool that's included in the Docker image. That's called audit wheel. Audit wheel is going to analyze the wheel and have a look at all of the dynamic, the runtime dependencies of the wheel, right? And it's going to decide whether or not it's eligible for like a many Linux platform tag. And if yes, it's going to compute the right version of glibc. So if we have a look at that output, this is just a kind of analysis out of audit wheel. It's not creating any wheel yet. It's just printing some information about the wheel. The most important piece of information that we have is that this wheel here, the wheel that we just built, is eligible for the tag many Linux 2.17 and then the architecture, right? And that 2.17 is the version of glibc that is currently installed inside that Docker image. And so this means that our wheel is expected to be usable on any GNU Linux system that has a version of glibc that's equal or greater than 2.17, okay? But now, if we actually want to create that new wheel with the right tag, we use audit wheel repair. And so we're going to, and then we give our wheel. And so this is going to create a new wheel based on the original one. That's done. And now if we look at the files that we have a new directory called wheelhouse. And then inside that directory, we've got that wheel with a very long name, but we do have the right tag, Linux 2.17. So now if we put that on PyPI, then when pip goes to look for wheels, it can tell that this wheel is going to work with glibc 2.17 onwards. Right. Good. There's one thing I kind of glossed over though. If we go back to our original wheel, so not the repaired one, like the one that we just created first. If I kind of unzip its content, and then now I want to kind of list all of the dynamic dependencies of the extension module that it contains, we see that our d.dot extension module has dynamic dependencies on several things, several libraries, and most of them we kind of expect to be found on any Linux distribution. You know, you've got libm, you've got libgcc, libc, all of these we kind of expect to be found on our friend's computer. But we do have this lib openblast here. That's the C library that our extension depends on, that we had to install. And so definitely this, we don't expect our friend to have it installed on their computer. So what's going to happen when we give our wheel to our friend, they're going to install it with pip. It's going to work fine. And then as soon as they're going to try to import the Python extension, things are going to break, right? Because it's going to say, oh, I can't find lib openblast because you don't have it on your system. How do we make our friends' life easier? Well, remember that the wheel is an archive, right? It's a zip archive. So what if we just take that .so file, libopenblast.so, and we just bake it into the wheel. We just put it inside the archive. Why not? That's actually a good plan. There's one more thing to do, is that if we do that, we somehow have to register in the extension module the information that the dependency, libopenblast, the dependency is located next to it inside the wheel. Because when our friend imports the module, then the dynamic linker is going to want to find that dependency. And the wheel is not part of the standard set of locations where the dynamic linker is going to look for. So we have to tell it that, wait, you can find that dependency right next to the file is in the wheel. There's a way of doing this. You can actually modify that shared object to record that information inside it. It's, you know, it's a bit technical, and I don't want to go into the details. And actually, I don't have to, because audit will repair, which I called earlier, audit will repair is actually doing the job for us already. And so if I use audit will repair is going to actually identify the libraries that we don't expect people to have, and it's going to copy them inside the wheel, and then it's going to modify that compile extension to actually record the location of the wheel. And so now I just want to show you, give me a second. If I now extract the extension module for the repaired wheel, and well, first of all, you see that now there's a new thing in there. We've got that library inside it. And if we asked to list the dependencies of the extension module inside the repair wheel, so we use LDD again, but now on the repaired wheel, then we can see that libop and blast is there, and now it's found not in the Docker images, or in the one. It's not the one that we installed with apt. It's the one that is contained in that directory, literally inside the wheel. So what that means is that we now have a Python wheel that is completely self-contained. We have dynamic dependencies in it, and it's also guaranteed to work on any Linux systems that has glibc equal over 217, right? So roughly any Linux distribution that comes after 2014. And we can give that to our friends, and they just install it, and it works. They don't have to install anything except from the wheel itself. Okay, that's basically all that I wanted to tell you today. If I forgot to actually start the clock watch, so I don't really know how much time I have, but if I had a bit more time, I would tell you about CI bidwill, which is a little Python package that you can install on your continuous integration system. And that's going to take care of building wheels for you, for any Python version, for any operating system, literally anything that you want to support. Now, that problem of runtime dependencies, you would also have it on macOS and Windows. And so on macOS, there's some kind of an analogous software to audit wheel, and that's called delocate. So you can have a look at that if you're using macOS. On Windows, I haven't found any kind of analogous utility. For now, I think the solution is to just build your dependencies statically into your wheel. If you are working on Python projects, I think, well, I encourage you to actually distribute wheels for your project and to just dig a little bit deeper into that topic. I have all of the material for this talk are available in that repository, and that's with the provided material of this talk. You can find the example, and you can find a list of references. Generally, building wheels is a sort of a complex process for your computer, but for you, the Python packager, not as much. It's not that difficult, and that's thanks to the work of people behind Linux, behind Delocate, behind Audit Wheel, behind CI bidwill. And so, with that, I'd like to thank these people. Thank you for attending that talk, and happy wheel building.
Excellent, thank you, Thibaut. That was fantastically interesting talk. Thank you. I've learned a lot there. We've got quite a few questions to pop through before we have a quick break. The top question is, how do wheels compare to conda packages? Does conda solve the compiling on Linux problem?
Yes, yeah. Thank you for asking that question. That's that's a really interesting discussion. Yeah, conda does. Basically, the short answer is with conda you don't really have to worry about any of that when you're installing the package, because I think I was not using Python at the time, but when conda started, I think one of the main motivation for conda actually was that problem. Was that people wanted to, pip install numpy, and then people would get errors because they don't have any C libraries installed, and it would be really difficult. So the people over at Continuum Analytics, that was called at the time, I think, they basically solved that problem early on. But they were a company, and so the Python community kind of caught on a bit later with the wheel format. There were format before that with eggs and stuff, but then wheel kind of got the Python with pip up to date with conda on that front. So yeah, if you're using conda, it's dealing with that already. You can just you're getting all of the compiler dependencies. Fine.
Okay, I think you may have touched on this next question already with the extra bit you added on the end there. Is there a way of setting up some kind of wheel factory for all the architectures you want to support?
Yeah, you can do it yourself if you want, but you can also use that CI build wheel package. Actually, when I started working on that on a Python project building wheels, I did do it myself until a colleague of mine just said, "Oh, why don't you use CI build wheel there?" And it literally changed my my work life, let's say. So yeah, just have a look at CI build wheel, and then it's very easy to use. The documenters, it's great. You just it supports GitHub Action, it supports Travis, it supports up there. I think you can think of.
Cool. I don't know. I guess the next one might be a one-word answer. You mentioned you need to make a separate wheel for each architecture and OS. Do you need one for each version of Python?
Yes, you do. Okay. Yeah, because you need to when you compile, you need the Python header files, and so they are. Yeah. Okay.
Next one's great talk. Any thoughts on handling C++ dependency versioning? In your example, BLAS, but also stuff like CUDA.
Yeah. Well, in my example, I use BLAS, but I guess if you have a dependency on the CUDA C library, it would probably work in the same way, right? I use BLAS, but it was kind of like an example. You could replace BLAS by any C library. Although BLAS was interesting because it's basically what happens in NumPy. NumPy has dependency on BLAS, so that's okay. Yeah. I hope that answers the question.
Okay, it does. I'm thinking. Let's have a look. See what we've got the last two. With your wheel factory question, can you? Is this something you could incorporate into continuous integration?
Yeah. So CI build wheel, it's literally designed to work on continuous integration. Actually, they don't recommend that you run CI build wheel on your local computer because it's using super user privileges. So yes, the answer is yes. It's meant to be used on continuous integration systems.
Okay, super. Next question was, you can see you want to use wheels on Windows, but what's the problem with building packages from source on Linux?
Well, the problem is that, in this case, it's fine because you just have to apt install OpenBLAS, and then, it takes a second. But the problem generally is that if you have dependencies, a lot of these dependencies, then people have to, fan in themselves, or what package do I install? It's a bit tedious. Fine. Some of them might not be. For instance, I'm working on a project at the moment, and we have a dependency that we need to compile ourselves. It's a big linear algebra library, and that depends on other things, and so you literally have to do it yourself, using make, and so that's completely out of reach of many of our users. So we don't want them to have to do that. Then the actual real problem is that then on Linux, every Linux distribution, packages a different version of packages, and so you might have users that install a specific version through a package manager of that library of, say, BLAS, and that version is actually not compatible with the one that you use to build your package. So you have a real problem here. So in some cases, users might get away by just installing a package from their package manager. That's fine. That's not really safe. So you might have trouble in the future. If you want to sleep well at night, then you should make sure that your dependencies are included in the wheel, and then you just the wheel is a little bit bigger, and then that's fine.
Yeah, well, thank you. And is creating wheels with Fortran extensions as straightforward as C ones, even with Windows?
Yeah. I think so. I mean, in terms of Fortran, it's the process is the same. You have to use something called F2Py. I've never done it. I encourage you, if you're interested in that, you have a look at NumPy because they do use it. Then the problem is that it's just you need to compile your C code, so it's fairly independent to actually writing Python. So it might be hard on Windows, but it's not related to the fact that you want to build a wheel. It's just because it's hard to compile your Fortran library on Windows. So unfortunately, you have to find a way to do that. If you do, then you can build your wheel.
Okay, brilliant. Thank you very much for that. I think it's time we went for a bit of a comfort break at this point. So I think we'll have a 5-minute break now. And be back in 5 minutes for Jamie's talk about GPU accelerated Python. Hi all, welcome back everyone. Hope you've had a nice break, got yourself a cup of tea, settled down. Without further ado, I'll hand you over now to Jamie Quinn from UCL, who's going to give us a case study on some GPU acceleration. Jamie.
Yes, can you hear me okay?
I can hear you fine.
Good. Okay, let's share these, and you can see these slides fine?
I can see that fine as well.
Okay, yes. So today, to this nice Python audience, I want to talk about some work that I've been doing programming a nice little fluids model in Python using some GPU stuff, specifically using spectral methods. And I'll go into why those are particularly useful to run on GPU. So yeah, the case study is this program Melvin.py. As I said, pseudospectral GPU accelerated. It's really a framework for numerically solving different problems, 2D problems in fluids. If you want to play about with it, go ahead. It's up there on my GitHub. And so this is just a wee example of the kind of simulations that you can run with it. But why Python? I mean, originally I kind of just wanted to start playing about with Python, specifically GPU accelerated libraries, and see what was possible in Python and really see what the kind of landscape was. And so fundamentally what I found was that it was really easy to prototype. It had a lovely fast iteration cycle, which meant I could, prototype really quickly, as well as it being really straightforward. Python generally, having been part of the Python community for a while now, I think it's really easy to just fall into the collective good practice that the community generally has. Python being so popular, a lot of folk have written accelerated libraries or replacements for existing libraries. I'll go into that. And in terms of kind of thinking about, well, what do we actually want to teach to students, and particularly students of high performance computing, is Python a good language to teach there? And I think, students want to learn and use Python simply because it's so popular for other things, data science and web development. As we've seen with Django. So kind of fundamentally what I want to try and convince you is that Python is a wonderful language for prototyping research codes and for teaching kind of GPU accelerated numerical methods. So I'll dive into each of these little bits. So just to give you a taste of all the different features I managed to shoehorn into Melvin in quite a short period of time. We have various different types of spatial discretizations, different boundary conditions, different ways of handling nonlinear operators in the equations, different ways of time integrating the equations forwards in time, and what's called implicit handling of the diffusion operator, which helps with stability. Fundamentally, Melvin is designed to be extensible, but it's Python's strengths in essentially being able to write first-class functions that can be swapped in and out, and having a whole load of features that allow straightforward kind of plug-and-play algorithms. So as much as it was easy to prototype these kind of different numerical methods or different features of Melvin, it was also extremely quick. Of course, as many Python projects do, it started as a Jupyter notebook. So, you have that ability to run single cells. You don't have to run the entire code. You can run single cells and really quickly kind of iterate over a single numerical method. And not only that, but you can also visualize it in the same notebook. You can have matplotlib printing out some nice visualizations so you're in the right ballpark. And then Melvin moved to just a collection of scripts. I managed to add a few little tests with PyTest and that kind of thing. And then it turned into a fully fledged Python package. So it was this nice cycle at each point, allowing me to refine both the numerical methods, which is important in high performance computing because you want your numerical method to be as suited to your problem as possible. You can make a ill-suited numerical method as fast as you want. It's still not going to be great if you haven't chosen the right method to begin with. So it allows refinement of the numerical method. but it also allows refinement of the interface, both in terms of how the different components of any software fit together, and also how the user interacts with that. So that went through a lot of iteration as well, throughout this entire process. And the kind of good practices that I think I've picked up and managed to put into Melvin is, of course, version control. It's fully on GitHub. Some nice parameterization with JSON, obviously very straightforward in Python because Python has its JSON library. It's great. You can have community contributions through GitHub. A lot of the testing and linting, in fact, all the testing and linting is entirely automated with GitHub Actions. So you've got that continuous testing there. The type, PyTest, and some static analysis, both with Flake and Black. So onto the actual meat of the GPU stuff. In terms of actually accelerating the code, I used a lovely library called CuPy, which is a drop-in replacement for NumPy. So if you just write your code initially in NumPy, you can then essentially just comment it out and change this one import statement to import CuPy instead of NumPy. And then you get access to all of CuPy's functions, which are essentially just recreations of NumPy and a lot of SciPy functions as well, but accelerated. They're all written in CUDA, and it's accelerated on NVIDIA GPUs. I think they have some support at the moment now for AMD GPUs, but I think that's still quite early days. So you also have access to multi-GPU stuff through CuPy in some cases. Sometimes it's a little bit tricky. It provides really easy integration with other libraries. I'll go into other alternatives in a second. And very nicely, you can actually still profile CuPy with NVIDIA's Insight, which are their suite of profilers and optimizers. So that's very nice. I should say it's not necessarily always as simple as just changing an import statement, because the fastest GPU codes will always have all of the working memory on the GPU. There is some memory transfer things that you have to just be careful about. So some alternatives to CuPy. You've got common ones like JAX, which is a very similar idea. It's a NumPy replacement. It's supported by Google. And that also has some differentiation into it. So you can take your simulation and actually differentiate it, and then that can be quite straightforward to be popped into a machine learning framework, for instance. So, and that's a really interesting active area of research at the moment, is how, replacing bits of simulations with surrogate neural networks or whatever, different machine learning algorithms. And so being able to fit a simulation into the pipeline like this is pretty damn useful. You've also got Legit, which is NVIDIA's own NumPy replacement. I haven't really played about with this. I think it's still in beta. There's a lower level, you've got CUDA-Python, which is NVIDIA's own low-level CUDA library for Python. You've also got PyCUDA, which is an independent low-level library. And you've got Numba, which is a kind of funny beast. I'm sure many folk have played about with it. I actually haven't yet. But in essence, it's a just-in-time compiler, which means you say which functions you want it to compile, and then it'll compile those just before it runs. So you get a speed up even on the CPU when using Numba. But then you can also write CUDA kernels, and actually you can write it in a funny subset of Python rather than writing it directly in CUDA C, which can sometimes be quite intimidating. What's nice about CuPy here is I think it's Numba actually that provides a really nice kind of glue layer between the different libraries. So if they're not interchangeable, like JAX and Legate, they're usually interoperable. So if one library does not provide the features that you need, well, you can actually shift your array or whatever structure you're using on the GPU, you can shift that into a different library with great ease and use the functionality that you need from a different one. So let's take a short break to talk about some nice results I've managed to get from Melvin. So this is simulating the Navier-Stokes equations. It's just a nice little vortex ring that kind of smooshes itself around. So you see some nice behavior there. And so this has got doubly periodic boundary conditions. That's pretty standard for spectral methods, because the spectral part of spectral methods essentially means that you solve the equations in Fourier space. You don't solve them in some sort of physical space. You take essentially a Fourier transform of that and then solve the equations in spectral space, and you get better accuracy in a lot of times, although there are some quirks with non-linear terms. But I won't go into that. This is not for a fluids audience. And we've got another little classic instability. This is the Rayleigh-Benard convection, where you've got a hot plate at the bottom and a cooler plate at the top. And the fluid gets heated and moves around. And so this is showing off that you can also have these solid boundary conditions at the top and the bottom, and that's provided with a finite difference spatial discretization as well. So it's just Melvin being able to do slightly different boundary conditions there. And this is in fact a whole different kind of equations. This is the magnetohydrodynamic equation. So this adds a magnetic field equation into the mix. And so this is modeling perhaps like a plasma in the solar atmosphere or something like that. And this is actually what I designed Melvin for, which is modeling these what are called thermohaline staircases in the ocean. So where you've got gradients of temperature and salinity kind of competing against each other, you get this on the left, you get what's called salt fingering. Eventually that evolves into what you see on the right, which are these nice big staircases. Now, what's difficult about this is the different scales at which things happen. You see on the left, you've got these very, very small fingers that you're wanting to resolve, and on the right, you've got these large structures as well. So I think it's interesting that the paper that I've came across that first seems to have simulated this ran essentially this simulation in about 2003, and it was over hundreds of nodes. It was, a big MPI Fortran program. I think it's quite amazing just the how technology moves on when you have me being able to now simulate this in, I think this was about a day or so on the GPU that's just attached to my home computer. It's nothing special. Which just kind of goes to show how powerful GPUs can be, but also the progress that we've made. So I'll talk a little bit about how I validated the code and a little bit about its performance as well. So the validation test was 1,000 time steps of what's called a Taylor-Green vortex. That's a known analytical solution to the Navier-Stokes equations. And so the code was run using double precision, the highest order time and space discretizations that I could use, although this particular problem actually only tests the diffusion operator, which is first order here. So you'll notice that in the error rates. And essentially, here you can see the different configurations that I used, exactly the time that it took to run and the error compared to this analytical solution. And you can see at the very top, we've got the CPU version that's just using naive NumPy. It's not been optimized. I'm sure you could get a much faster speed, but this is just a naive run. And just by changing that one line, that import QPy instead of NumPy, we go from 143 seconds to 11. Which is great. That's exactly what you expect from these kind of experiments. Because the spectral method uses fast Fourier transforms, they're very well suited to the GPU. So you end up with a really quite nice speed up. When we also move from time order of 4 to 2, we actually see no difference in the error rate, and that is very probably because this is not really testing the diffusion operator. But we do get a small speed up. We also get a similar speed up by changing instead the spatial order from 4 to 2, keeping the time order at 4. And then as well, we get a great speed up just by switching from double to single precision. And that's just because GPUs are typically very, very good, much, much quicker at dealing with single precision calculations than double. So you're nearly doubling your speed just by switching from double precision to single precision. And here you do notice a small difference in the error, but it's minuscule. I think with more complex problems, you might see a greater difference there, but I haven't found in my testing. I usually run in single precision and just check in double precision sometimes. And if you combine all these speedups, you get an ultimate speed of 4.43 seconds, which is 30 times, well, over 30 times greater than the original CPU version, which is quite, I think, astounding, but also quite in line with what you'd expect. And of course, the CPU version is not optimized in any way. So let me talk about a little bit about lessons I've learned and some alternatives to Python in this kind of space. So essentially, one of the big things was the fact that it's not compiled means that it can be often unsafe. You're passing things into functions, and that function has no real idea of the type. So static analysis has been quite important. Just being able to use even tools like Flake and Black are particularly helpful at spotting things that might not be quite right, that would otherwise have been spotted if you were working in, say, C++. The compiler would manage to catch a lot of these errors. As well, compiled languages tend to be much faster, simply because it's got time to add optimizations into the code. And so Python generally is quite slow, but offloading a lot of the computations to the GPU speeds it up greatly. I found for this kind of stuff, the speed was good enough. I wrote a kind of comparable C++ code a few years ago, optimized that quite a lot, profiled that, did a lot of that kind of thing. And that's only about 1.5 times quicker than currently Melvin is. And I haven't done a lot of optimization to Melvin yet. I found the flexibility was definitely worth it. The fact that I could switch up different numerical methods and change things around, that was worth that difference in speed. And ultimately, I can go further. You know, I've moved from NumPy to CuPy. That's really the first step. I can move to Numba, which provides just-in-time compilation, and I can write some CUDA, or I can move totally to CUDA Python and go as low level as I want. So some alternatives. You've got accelerated C++. It has a number of different options for targeting the GPU. C++20, I haven't used a lot of it, but some people say it's nearly as simple to write as Python. That could be a good contender. And as I said, yeah, the Melvin.py is only about 1.5 times the runtime of my equivalent C++ CUDA version. So what about Julia? Of course, it offers impressive performance with kind of similar Pythonic ease, and it's a very modern ecosystem. However, it's still a relatively young language, and it's a new paradigm to learn. Instead of having object-oriented structures that we're all kind of used to, and the multiple dispatch system is a little bit different and requires a little bit more thought to get used to. And for now, it seems like there's fewer opportunities beyond high-performance computing or machine learning in Julia. You know, it hasn't really hit, say, the web development sphere as much as, say, Python has. So in conclusion, I say Python is rarely as fast as Fortran and C++, certainly when you take the time to optimize it, and a lot of the profiling tools are built for optimizing C++ and Fortran, so it's maybe a little bit more streamlined. But the flexibility makes it an ideal language for prototyping GPU-accelerated numerical codes, for figuring out which numerical methods are going to work best for the problem, and also which are going to be best for the GPU architecture. And I think it makes it an ideal language for teaching numerical methods, particularly in HPC, particularly when students already know Python, which is really quite common. So thank you very much for listening.
Brilliant. Thank you, Jamie. We have a couple of questions for you. The most popular one is, which of the different alternatives to CuPy do you think will still exist in 2 or more years' time? What's the best choice for software that will live for many years?
Yeah, that's a great question. I think, I mean, CuPy, I think, will be around for a while. It's provided itself a really nice niche. I think Numba is doing something very unique in the space, and so I don't think anything else will come along and manage to trip it up. ultimately, CUDA Python was just released. NVIDIA's own CUDA Python was just released, I think this year or maybe last year. So that's very new, but I think because it's backed by NVIDIA, I think that'll be around for a long time, although it's lower level. So I think for software that will live for many years, probably NVIDIA's offering is best for future-proofing. But I would certainly say CuPy or Numba seem to be in my head well supported. Of course, Jax has Google support as well. So they're all big players. I don't think any of them are going to go away.
Okay, brilliant, thank you. And what are your future plans for your code? Do you plan to merge it into a more established package or run it as a standalone project?
Another great question. I struggle with this question myself because I can't remember the name of the code now, but there is a similar code in Python that doesn't have a GPU component at the moment. It has lots of MPI stuff, and so you can run it across many nodes, but yeah, it's not targeting GPUs as far as I can tell right now. So I think, yeah, maybe kind of applying the stuff that I've learned there could be a good use of Melvin. Maybe not merge it itself, but yeah.
Okay, cool. And thinking back to the last talk, how easy is it to package and distribute the CuPy code?
So using wheels, actually, ironically, it's very difficult. Or not very difficult, it's just a bit finicky. You have to specify the version of the version of CUDA that you want to target with CuPy. So that makes it a little bit less reproducible. You know, if you've got a dependencies list, you have to ask the user to change it depending on which CUDA version they're actually running on their machine. But actually, without using wheels and requiring just saying, oh, just install CuPy, it doesn't matter, you know, figure out exactly which CUDA version yourself, that seems to work actually very well. So yeah, in essence, if you're going to distribute something using CuPy, don't bother with the wheels.
Okay, cool, thank you. And what are the advantages of GPU over MPI or multi-threading in this particular case?
So in this particular case, it's essentially the access to very fast Fourier transforms. And GPUs are really good at it. It's got the data locality. As long as your entire simulation fits on one GPU, which I guess, you know, isn't true for the Met Office's climate models and things like that, but for these small, especially 2D simulations, yeah, it can be very, very fast. I think for MPI, it's definitely data locality. You know, how you've got, you know, 1,000, 2,000, even 5,000 cores all running on one little box, and you have, you know, up to, I think some GPUs have, you know, 30 gigs of memory sitting on them. So you can run decent simulations without worrying about MPIs, messages, and that kind of thing. Multi-threading as well, you just have access to more cores. So if your problem is such that you can handle all of those cores, that you can make use of all those cores, then I think GPU is probably going to be a really good option.
Okay, thank you. Another question just come in. Have you tried scaling your programs up? What are the size limits problems?
Problem size limits.
Problem size limits, yeah.
When do I get tired of my program running? I just want to close it down and do something else, or actually use my computer when I'm running the GPU on my home computer. Yeah, in terms of resolutions, have I run it as much as, I think probably at the moment 8,000 by 8,000, a box of 8,000 by 8,000 spectral elements, that kind of resolution. Again, it depends what physics you're working with, but if I were to run, say, the thermohaline staircases model, that's probably the most computational intensive thing I'm doing at the moment, and to probably resolve all the features of that, yeah, you're required to get up to kind of the thousands or even the tens of thousands of grid points. And they take maybe on the order of 12 hours a day, depending on which GPU you're using.
Okay.
It's hard to answer that question
Yeah, no,
because it does depend on like even timescales. You know, does your problem need a long time to settle into a certain behaviour or something? But yeah, I hope that answers.
Thanks. Well, thank you very much, Jamie. Thank you for your talk.
Cheers.
I've got a couple of things to go with, so that's really good. Thank you. And I'd just like to thank everybody this afternoon for coming along to these walkthroughs and talks, and our presenters, Terry, Thibaut, and Jamie. And hope to see you maybe later on or tomorrow in the venue in Gathertown. And then tomorrow at 10 o'clock, we've got a workshop session, Flame GPU 2. If you haven't signed up for that, could you do so, please? And then in the afternoon tomorrow, we've got the excerpt Q&A session. So hopefully see you around at one of those things. Thank you very much. See you tomorrow.